the hyperbolic functions. The hyperbolic functions are a set of combinations of e to the x and e to the negative x that occur frequently enough in mathematics and related fields that they've been given special names. So, for example, the hyperbolic sine, which is denoted sin of x, is the function that can be expressed as e to the x minus e to the negative x over 2. And here in red is the graph of hyperbolic sine of h. And so it is the graph in red. And notice that it is bounded by the functions 1/2 e to the x, which is in blue, and negative 1/2 e to the negative x, which is in green. Similarly, we define the hyperbolic cosine of x as e to the x plus e to the negative x over 2. And again, that's the graph that's in red in the middle here. The hyperbolic cosine is bounded by e to the x over 2 and e to the negative x over 2. Notice that the hyperbolic sine is an odd function, and the hyperbolic cosine is an even function. Remembering what those mean. Odd function, f of negative x is equal to negative f of x, and an even function, f of negative x is equal to f of x. And the hyperbolic tangent, denoted tan of x, is equal to hyperbolic sine of x over hyperbolic cosine of x, and could also be noted as e to the x minus e to the negative x over e to the x plus e to the negative x. But notice that there's a similarity there. We remember from trigonometry that the tangent of a value can be represented as its sine divided by the cosine. And we see a similar expression with the hyperbolic functions. And we can also define the hyperbolic cosecant, the hyperbolic secant, and the hyperbolic cotangent similarly. Here are some hyperbolic identities, and you should notice that a lot of them are quite similar to what we saw in trigonometry. So remember, say for example in trigonometry, we learned that sine square x plus cosine square x is equal to 1. And notice that the analog in hyperbolic functions, hyperbolic cosine square minus hyperbolic sine square is 1. Also, we learned that 1 plus tangent square x was equal to secant square x. Now, in hyperbolics, 1 minus hyperbolic tangent square x is equal to hyperbolic secant square x. So they're similar, but not exactly the same. Mostly the signs, the SIG and S, are different. The sum identity for the hyperbolic sine is similar to the sum identity for the traditional trigonometric sine. And the sum identity for the hyperbolic cosine is again similar, but note the SIGN difference as compared to the trigonometric identity. So now we'll look at a couple of identities and verify them. So here we're asked to verify the identity that the hyperbolic cosine subtract the hyperbolic sine of x is equal to e to the negative x. Alright, so I'll start with the left-hand side, the hyperbolic cosine minus the hyperbolic sine. Using their definitions, the hyperbolic cosine is e to the x plus e to the negative x over 2. The hyperbolic sine is e to the x minus e to the negative x over 2. Now, since I'm subtracting fractions with a common denominator, I can write that as a single fraction with the denominator and subtract the numerators. Distributing the subtraction, I have e to the x plus e to the negative x, subtract e to the x, add e to the negative x, and that's all divided by 2. Combining like terms in the numerator, notice I have an e to the x and a minus e to the x, and those will go to 0. I have a plus e to the negative x and another plus e to the negative x, and so that would give me 2e to the negative x over 2, which is simply e to the negative x. And we verify the identity. Verify the identity that hyperbolic cosine of 2x is equal to hyperbolic cosine square x plus hyperbolic sine square x. So I'm going to use the fact that the hyperbolic cosine of 2x would be equal to the hyperbolic cosine of x plus x. And now I'll use the sum identity for hyperbolic cosine of x plus y. And so then, now instead of x and y, there's x and x. And so that would be hyperbolic cosine of x times hyperbolic cosine of x plus hyperbolic sine x hyperbolic sine x, which simplifies as hyperbolic cosine square x plus hyperbolic sine square x. And again, this completes the identity. So now let's look at how we can differentiate the functions, at least a couple of them. Let's say we wanted to differentiate y equals the hyperbolic sine of x. Well then, y would equal, from the basic definition, y would equal e to the x minus e to the negative x over 2, which is the same as 1/2 of e to the x minus e to the negative x. So then the derivative, y prime, would be 1/2 times the derivative of e to the x is e to the x minus, and the derivative of e to the negative x is e to the negative x times negative 1. And so y prime would be 1/2 of e to the x minus a negative, that's plus e to the negative x, which is equal to e to the x plus e to the negative x over 2, which is a hyperbolic cosine of x by definition. So the derivative of the hyperbolic sine is the hyperbolic cosine. Well, that sounds familiar, doesn't it? So now would be a good time to try one on your own. Differentiate the hyperbolic tangent of x. And a good idea would be to use the fact that the hyperbolic tangent is the hyperbolic sine divided by the hyperbolic cosine. So why don't you pause and try this on your own. Alright, so I'll use the fact, as I mentioned, that the hyperbolic tangent is the same as the hyperbolic sine of x divided by the hyperbolic cosine of x. So now, using the fact that we have hyperbolic sine over hyperbolic cosine, I can differentiate with respect to x and using the quotient rule. So then, y prime would be the lower function, that's hyperbolic cosine of x, times the derivative of the numerator. The derivative of hyperbolic sine is hyperbolic cosine x. We just showed that in the previous slide. Minus the upper function, hyperbolic sine x. And now the derivative of the lower function. Okay, so I didn't prove it, but it turns out that d by dx of hyperbolic cosine x is hyperbolic sine of x. So high d low would end up being a hyperbolic sine of x. And then in the denominator, we would have hyperbolic cosine square x. So then this is hyperbolic cosine square x minus hyperbolic sine square x over hyperbolic cosine square x. Recalling one of our identities for hyperbolic functions, hyperbolic cosine squared minus hyperbolic sine squared is 1. So we have 1 over hyperbolic cosine squared of x, which is hyperbolic secant squared of x. And that should sound familiar as well. Remember that the derivative of the trigonometric tangent, right, just tangent x, was also secant square. And so we see again an analogy in the hyperbolic functions. All right, so here are the derivatives of the hyperbolic functions. We proved the first and third of them, that the derivative of the hyperbolic sine was the hyperbolic cosine, and the derivative of the hyperbolic tangent was the hyperbolic secant square. And you should see that these are quite familiar. The only differences would be some changes in signs, SIG and S. And so you should probably commit these to memory, but again, the only difference is in some of the signs. All right, so let's differentiate y equals hyperbolic cosine of the natural log of x. All right, so then y prime would be the derivative of the outside function. That would be the hyperbolic sine of the inside function times, by the chain rule, the derivative of the inside function. And so y prime would be sine, hyperbolic sine, natural log x. The derivative with respect to x of natural log x is 1 over x, so I would write that over x. Differentiate y equals the hyperbolic sine of the hyperbolic cosine of x. Then y prime would be the hyperbolic cosine of the hyperbolic cosine of x times the derivative of the hyperbolic cosine of x by the chain rule. So then y prime would be hyperbolic cosine x, hyperbolic cosine of hyperbolic cosine x times hyperbolic sine of x. Evaluate the integral of the hyperbolic sine of 1 plus 4x dx. Using the substitution, u equals 1 plus 4x, and du would equal 4 dx. So I need to bring in side of 4 and outside of 1/4. And so then this would become 1/4 integral hyperbolic sine u du. So that's 1/4. Well, since the derivative of the hyperbolic cosine is the hyperbolic sine, then the antiderivative of the hyperbolic sine is the hyperbolic cosine. And so then 1/4 hyperbolic cosine of 1 plus 4x plus a constant. Evaluate the integral of the hyperbolic tangent of x dx using the fact that the hyperbolic tangent is the hyperbolic sine over the hyperbolic cosine. Now I'll use the substitution. U equals the hyperbolic cosine of x, just like I did with the traditional tangent. Then du would be the hyperbolic sine. And so then I now have the integral of du over u. And so that's the natural log absolute u plus a constant natural log absolute hyperbolic cosine u plus c. Now remembering that the hyperbolic cosine, that should be an x, not a u. If you remember the graph of the hyperbolic cosine, it's entirely above the x-axis, so therefore it's always positive, and so we really don't need the absolute value bars here. Well, let's look at an application. Here we're told that the Gateway Arch in St. Louis was designed by Eero Saarinen and was constructed using the equation y equals 211.49 minus 20.96 hyperbolic cosine 0.03291765x for the central curve of the arch, where x and y are measured in meters and absolute x is less than or equal to 91.20. We're asked to graph the central curve. All right, so I'm going to use a calculator for this because this is a fairly difficult exercise. So on the TI-89 type calculators, if I go, put it on, some stuff here. I go to my y equals screen. Oh, I'm in a different mode. Sorry, let me switch my mode back to function mode. Enter, and enter to save it. Alright, so I actually have it in there. So my y equals 211.49 minus 20.96. Now the hyperbolic cosine, to get to that, you have to go into the math menu. So that's second and the 5 button. And if you scroll down in the math menu, you'll eventually get to the hyperbolic option. And if you press right, and there's your hyperbolic function. So I'll go in for hyperbolic cosine, enter, and that brings it up on the screen. And 0.03291765x. Close that off, hit enter, and it brings it up. Now we're told that x, absolute x, is less than 91.20. So when I'm setting my window, you'll notice I got negative 92 to 92. That'll include negative 91.2 to positive 91.2. And I'm guessing that, based on the curve, I see that 211.49. So that, if we sort of think of that as a transformation, our standard curve, let me go back, let me look just at the screen here. Our standard curve, our cosine, our hyperbolic cosine, has been widened, been moved up, flipped over, and scaled. And so I'm thinking that my center point of the hyperbolic cosine curve has been moved up 211. So when I go to my calculator, wrong calculator, sorry. When I go to my calculator, notice how I've adjusted the y max to 220, and that'll take into account that 211.49. Alright, so now if I hit the graph key, I see this curve that looks like a parabola, but is not a parabola. It's actually called a catenary. C-A-T-E-N-A-R-Y. So there's the catenary curve. Now, on the TI, if you're working on a 383 or 84 calculator, it's a little tougher. There is not a nice hyperbolic submenu to work with. So if you go into your y equals screen, and you start typing in the curve, 211.49 minus 20.96, there is not a hyperbolic menu for you to go to. So instead what you have to do is go into the catalog. So second 0 brings up the catalog, and now I want the hyperbolic cosine. So I press C for cosine, which is this button. Notice it's already has the alpha ready. So I just hit the program button, and it goes to my C's. And now I just scroll down until I find the right option. So I want this one, the hyperbolic cosine. And again, then I'll just type in the point 0.032911765x. Set my window similarly, so negative 92 to 92 on the x's. I'll put a scale of 10 on the x's. And I'll have negative 10 to 220 on the y's with a scale of 10. I'll hit the graph key, and I get the similar curve. All right. What was the height of the arch at its center? All right, so for that, I can just trace. So on the 89, F3, 0, enter, and it's 190.53. No, that's not right. Hold on. It's not right about that. What is the height of the arch at its center? So at its center, that's where x is equal to 0. All right, so actually we could do this without the calculator, because we know that if x equals 0, then y would equal 211.49 minus 20.96 times a hyperbolic cosine of a bunch of stuff times 0. And so we end up with the hyperbolic cosine of 0, which, if we remember from the graph, the hyperbolic cosine of 0 was 1. So the y value would just be 211.49 minus 20.96. And we can now just do a simple subtraction. 211.49 minus 20.96 is 190.53. And that would be in terms of meters. Now let's verify that with the calculator. All right, so on the 89, if I go back to my graph, and if I just trace, so F3, and type in 0 for x and hit enter, and I get 190.53. And we'd have a similar instructions on the 84. At what point or points is the height 100 meters? So here I'd have to solve where is y equal 100. Now this can be done using inverse hyperbolic functions, but I'm not going to deal with that. We're not going to deal with the inverse hyperbolic functions. So instead, I'm just going to look at it from a graphical point of view. So on the calculator, I've got the graph, and I'm going to go back into my y equals screen, and I'm going to put in the second equation at y equals 100. Regraph. And notice that it appears to be even. I'm going to calculate, so under F5, I'm going to calculate the intersection. I'll calculate the positive intersection, so I'm moving to the right. 89. We could close hit enter a couple times for first and second, third, and last for a lower bound and an upper bound. So I'll make sure that you're to the left of where you think the intersection is, hit enter once, move to the right, go past where you think it is, hit enter a second time, and calculate the intersection at about 71.6. Alright, so at what points is the height 100 meters? So at the points positive or negative 71.56, comma 100. So when x is plus or minus 71.56, and again you would do something similar on the 84. What is the slope of the arch at those points? Alright, well the slope, if y equals that function, then y prime would be negative 20.96 times the hyperbolic sine of all of that times x, and then times the derivative of the inside would be that whole number again. Okay, so I'm going to go ahead and fill it in. I'll just put 0.03291765 0.032911765. Alright, so now, evaluating at x equals negative 71.56, y prime of negative 71.56. Alright, so I'll just use the home screen for this. So I would have negative 20.96. Now I need a hyperbolic sign. So again, I would go into my math menu. Hyperbolic sign of 0.03291765 times negative 71.56, and then I have to multiply that by the 0.03291765, and I'll hit enter on that, and it's about 3.6. And so that's the slope of the arch at that point. And we could similarly find that y prime of positive 71.56 is approximately negative 3.60483. Now, of course, if you are on these calculators, we have the graph. We can actually calculate those slopes under the math menu. So under F5 on this calculator, and I want under derivatives for the 89, if I move to the derivatives, I want dy dx, and I want dy dx at what point? Well, let's let x equal negative 71.56. And we find that dy dx is 3.60483. And we can do something similar on the 83 or 84 calculators. So if I bring up the 84, second calc dy dx, and again type in the x value, so negative 71.56, hit enter, and we get a similar value. Alright, so that concludes the presentation on the calculus of hyperbolic functions.